please record. Okay. Hey, today we are glad to have Dr. Salish Maharjan. He received his PhD in electrical and computer engineering from the National University of Singapore in 2020. He is currently a research assistant professor with the Department of Electrical and Computer Engineering at Iowa State University. His research interests include distribution system modeling, stability analysis, and optimization and control for techno-economic, operational, and resilience enhancement. He has received Best Paper Award at 2023 and 2025 IEEE PS General Meeting. So, and thank you, Dr. Rahul. Basically, he arranged the talk. We appreciate that. And again, thank you, Salish, for agreeing to give us a talk. And back to you.
Yeah, thank you. Today's presentation, the topic is distribution system, black start, and restoration using DERs and dynamically formed microgrids. So this seminar is based on my current research paper in IEEE transaction on smart grid. So I will be only covering part of this paper. For detailed analysis and results, I recommend you to refer this paper. Okay, let's start. So so what is black start? Black start is a procedure to restart a power grid after a widespread outages, right? So let's look at the black start process in transmission and a distribution. So firstly, like in a transmission, the black start resources are large generators, which includes hydrogen, hydropower, or like gas-fired generators. Whereas in distribution system, black start resources are typically diesel generators. And currently, we are looking whether distributed energy resources can be used as a black start resource or not. So in the transmission system, the cranking paths, the cranking paths are established by isolating the loads, right? And the cranking paths could be meshed in nature. But in distribution system, we cannot isolate the loads while establishing the cranking paths because most of the loads in the distribution system are not switchable, right? And we need to ensure that the cranking paths are radial in nature. And the generators in the transmission side have high inertia and high short circuit capabilities, but in distribution side, we have low inertia and low short circuit capabilities. So in the distribution system, traditionally black start has been conducted by using diesel generators. And these diesel generators used to have sufficient capacity, and utilities generally keep sufficient supply of fuels, right? So that's why establishing or like black starting distribution system with diesel generator is not a big deal because they can usually follow a certain switching sequence for the black start. But to do the same thing using distributed energy resources, it is challenging because distributed energy resources are typically small in capacity, and also they are distributed, meaning they are located at different locations, right? So that's and also DERs, some of them could be renewables and their generation could be uncertain. So the sequence of black starting has to be calculated at the time when we want to do a black start, right? So that's why a black start optimization become essential when we want to black start with DERs, okay? So let's look at the typical black start and load restoration process in a very simple distribution network with two grid forming inverters, okay, and many grid following inverters. So this slide. Okay, so this diagram on the right hand side gives you an idea how the black start is done. And for a very simple system, we don't have to optimize. We can simply use our intuition to determine a proper sequence for black starting the whole system. Okay. So firstly, there's a blackout in the distribution system, right? Because there's a transmission grid outage where it was connected. So there's no power in the, I mean, there's no active sources at that time when there's a blackout, right? So the first step is to switch on the grid, the black start resources. So black start resources in case of DERs are generally performed by grid forming inverters. So in this case, we have two grid forming inverters located at this point and this point, right? So we switch on them, and when we, after switching on them, we are able to energize the neighboring bus blocks. So in this case, we have 5 bus blocks, and then out of 5 bus blocks, we can energize B2 and B3 at a time. So basically, your grid forming inverters are helping to form a microgrid, and these microgrids are helping to energize the neighboring bus block at a time so that they can bring the grid following resources online. And these grid following resources will augment the power and energy capacity of the grid forming inverters and helping them to restore more loads. Okay. And then after that, the switching is again conducted independently at different microgrids to restore the loads as well as to bring the grid following DERs online, right? And at some point when we have energized all the bus blocks, we want to synchronize those two microgrids. The synchronizing helps to augment the power and energy capacity of individual microgrids. Okay, and this augmentation may be sometimes significant to restore some large amount of loads. And finally, when the transmission grid comes online, we want to synchronize the entire distribution system with the transmission grid so that the whole distribution system can run in this, can run continuously for long period of time. So this is the sequence we want to, we can think of for a very simple distribution system, but for a fairly complicated distribution system, I mean, we may not able to use our intuition to find out the switching sequence. So we need an optimization problem to guide us. What could be the switching decision that optimally help us to restore the load and enhance the black start? Okay, so basically the objective of the problem is to maximize the restored load considering the priorities, right? And there will are certain number of constraints for this problem, and out of which I am focusing only on 4 important constraints that are shown in the red color. So the first constraint is grid forming, inverter operation, and synchronization. So how to model them, that I will discuss in the next slide. And then switching constraint, dynamic radiality constraint, and frequency constraint. And the output or the decision of this problem is the sequence of energizing cranking paths. It could be a sequence of activating grid following resources, sequence of synchronizing decision, and sequence of load pickup. Okay, so let's talk about grid forming inverters, which are powered by battery energy storage. So we know so we are considering a virtual synchronous generator control based grid forming inverters. And for the virtual synchronous control, the diagram for the overall diagram of the control is shown on the right hand side here. So basically, VSM tries to mimic the characteristic of a synchronous generator. So that's why this kind of grid forming inverters are parameterized with inertia constant, damping constant. They have a frequency droop constant as well as voltage droop constant. So the overall control is to regulate voltage and frequency while delivering some active and reactive power output. Okay, but we want to look the grid forming inverters from a different perspective, mostly from a load flow perspective, because we want to model the black start of the whole distribution system. So we want to model the grid forming inverters in terms of voltage, output voltage, in terms of output active and reactive power, and also in terms of output frequency. That's the objective. Okay. So as I said, grid forming inverters, output voltage can be regulated and the frequency can be also regulated, right? So we want to relate those voltages in terms of active power or some parameters of the grid forming inverters, right? So now to comply with the branch flow model, we want to, it's a very, it's a very usual thing that we, instead of defining the voltage as a control variable, we define the square of the voltage as a control variable, right? So I'm doing the same thing in the first equation, and delta VCC is the small perturbation that is allowed uh, to allowed in this definition to allow the output voltage to change in some limits. And the limits are also defined. It is just like plus minus 5%. And the frequency. So the frequency, output frequency is defined in terms of active power output of the grid forming inverter and some parameterization such as damping coefficient and frequency droop coefficient and the capacity of the grid forming inverter. And this frequency has also limits from the security perspective. So that is the lower and upper limits. So let's talk about some dynamic frequency response. So from the security perspective, we also want to ensure that the rate of change of frequency and the frequency nadir are within the safe, secure limits. So we want to define the ROCOF and the frequency nadir based upon the initial QSS point and the final QSS point, so that we don't have to do a dynamic simulation to estimate these dynamic frequency responses. So you can see that the ROCOF is defined in terms of change in active power output of the grid forming inverters and in terms of inertia constant and the capacity. Similarly, the frequency nadir is also defined in terms of change in active power and other parameters. And we want to limit both of them to allowable limits, right? So the next thing is to evaluate whether those established constraints are accurate enough or not. So for that, what we did is we developed a RMS model of the grid forming inverter in a Dick-Silent power factory. And then we recorded the frequency response of these grid forming inverters when we subject load change to those grid forming inverters. So the load change this experimented was like we made a change of 1, 2, and 10 megawatts of load with the grid forming inverters, and their frequency response was recorded. And from this recording, we can easily measure what's the steady state frequency, what's the ROCOF, and the frequency nadir. And this same estimate was made by the constant we defined above, okay? And we found that the constant that we defined were able to measure those dynamic frequencies to an accuracy of above 90%. So for the planning problem, I think this accuracy is acceptable. And so with this verification, we ensured that those dynamic frequency responses equations can be can be used in the problem without requiring you to run the RMS simulation to measure these dynamic frequencies. So the next thing, important thing is modeling the synchronization of the grid forming inverters. So we know that while synchronizing, the grid forming inverters frequency set points should be allowed to change to synchronize with other grid forming inverters, right? So that's why we introduced a additional term in the frequency, which is basically the multiplication of a binary variable delta and the change in the frequency set point. So this delta is a binary variable, and it has to be set to 1 only during the synchronization period. So in the rest of the period, delta is 0. So delta F effect on the frequency is negligible, right? So I think, yeah, it's now it's important to decide when delta should be 1. And I mean, we'll discuss this in the next slides. So just keep in mind that when delta is active, then it allows the synchronization of the frequencies. Now, so the synchronization of the grid forming inverters can be done in various formats, right? So one format is simply keeping the frequency of the one grid forming inverter as it is and changing the frequency of the second, right? So that's generally a master slave synchronization process. But here we want to have more cooperative synchronization. So in the cooperative synchronization, both the grid forming inverters can decide at what frequency they want to synchronize. So that's why we use this last equation. So in the last equation, it simply says that the frequency of the grid forming inverter will be changed based upon any grid forming inverters willing to change this frequency reference. Okay, so let's talk about the switching structure of the distribution system. So we know that distribution system switches are not everywhere on the lines, right? So basically, there's a bus block structure of the distribution system. So bus blocks are isolated by switches, right? So when any of the switches is energized or switched on, basically it will energize the bus block, and all the lines and the buses within that bus blocks will also get energized, right? So this phenomena has to be reflected in a mathematical equation. So that's why this YBB refers to the binary variable that decides whether this bus block is active or not. So YSWI is the binary variable that defines the state of the switch. So it means that if there are multiple switches surrounding a bus block, so if one of the switch is active, then the bus block should be also active, right? So basically it is defining the same thing. And then this equation tells that if a bus block is active, then all the lines and all the buses should be also active. And the final constraint says that once the bus block is active, we don't want that bus blocks to be inactive again, right? Because we don't want to destroy the cranking path that has already been established, right? Okay, now let's talk about switches. So there are two types of switches. One is energizing switch, and the other is synchronizing switch. So energizing switch could be breakers, reclosers, or tie switches. And these energizing switches are switched on to energize a bus blocks. Okay, so during this black start process, the energizing switches can be at different states, right? So I define this state as state 1, 2, 3, 4, and 5. So basically in state 1, now, the adjacent buses of the switches are inactive. So it means that you cannot close this switch. And then in the state 2, one of the bus, state 2 and 3, one of the adjacent buses are active. So it means that we can close this switch. And other state 4 is after closing the energizing switch, the state 4 is says that both the buses are active as well as the switch is active. And the fifth state is that both the neighboring buses are active. So in this case, we cannot switch the close because although the buses are active, they could be at different phase, so we cannot close them, right? So we can represent all these 5 states in a mathematical equations, and those equations are shown by a bunch of constraints shown here. And then the important thing is this: when an energizing switch is closed, basically the frequency information at one block is also transferred to the another bus block. And if it is open, then the both bus block could have different frequencies, right? So these two different switching, different frequency, I mean, this condition can be also established by using this big M method shown here. I think the interesting thing is the interesting switches are synchronizing switches. So synchronizing switches are similar to energizing switches, but they are equipped with intelligent electronic devices that helps to facilitate synchronization. So synchronizing switches can also be used to energize bus block, but generally we don't employ synchronizing switch for energization purpose, but we employ them for the synchronizing of the microgrids because they can only synchronize the microgrids, right? So it also can have different 5-state as energizing switch, but the difference is in 5th state. So in the 5th state, when both the buses are active, the synchronizing switch can be closed. Okay, so we can model all these states by only 3 equations, and the frequency transfer condition can also be modeled. But it is not sufficient to model the synchronizing switch with only that equation. We also need to ensure that while closing a synchronizing switch, the voltage across the buses and the angle across the buses are sufficiently close, right? Otherwise, if they are not sufficiently close, basically when you try to uh, close at the condition when the voltage and angles are different, basically there's a short circuit, right? And the protection devices could trip, and we don't want this to happen. So we need to ensure that the voltage and angles are sufficiently close. So uh, now the voltage and angles, how to ensure that? Because in a branch flow model, we don't have a angle information, right? We only have a voltage information. So how to achieve, I mean, how to make a condition that this voltage and angle matching criteria is satisfied? So at the time of synchronization or at the time of closing switch, right? If we can ensure the power flow between these two buses are sufficiently small, right? Then we can say that voltage and angle between two buses are sufficiently close. And once you synchronize them, we should allow the power to flow between these two buses after the synchronization. So the condition of power flow in the synchronizing switch is dependent on the synchronizing instant. So at the synchronizing instant, the power flow should be constrained to be sufficiently small, and after that, it should be relaxed, right? So that's why we need to define synchronizing, we need to find out the synchronizing time step. So that's why I introduced this auxiliary variable Zij, which tends to be 1 when the synchronizing condition is met. And this based upon this Zij, a power flow constraint satisfying the power flow condition both at the synchronizing and non-synchronizing state can be defined. Okay, so next thing is radiality constraint. So radiality constraint it generally says that number of lines should be equal to number of buses minus number of root buses. So root buses in our case is defined by grid forming inverters, right? But the thing is that to allow the synchronization, we need to define. We need to those grid forming. Some of the grid forming inverters has to give up their root bus status, right? So let's go through one by one. So in the first equation, it's basically telling you the active status of the line bus. Active status of the line should be equals to active status of the bus buses and the active status of the root buses. So basically the first term is telling you that substation, if the substation is active, then it can also be a root bus. And then RT defines the active status of the grid forming, or let's say grid forming inverters and the substation. And the last term says that the grid forming inverters, they start as a root bus, but to allow for the synchronization, they give up the root bus status. So once the root bus status is given up, so they cannot become a root bus again. So this equation tells you that. Okay. Yeah. So as I told, when the two microgrids synchronize, one of the grid forming inverter has to give up the status of the root bus for agreeing. I mean, for the radiality constraint. Okay. So in that case, I mean, when one of the grid forming inverter give up the root bus, they have to initiate the synchronization, right? So that synchronization is enabled only when a binary variable delta is activated, right? So that's why the last equation, governs when a grid forming inverter gives up the root bus status and when delta is activated. So basically, dynamic relay constraint is connected with the frequency of the grid forming inverter by this delta. Okay. Yeah, so let's move to the case studies. So I have tested this this problem in a IEEE 123 bus system. So this system is modified to have a peak demand of 3.49 megawatt, and 60% of the loads are non-switchable in this system, and it comprises of 11 bus blocks and 11 switchable lines. Okay, and then the graph representation is shown here. And it has two blackstart resources, which is basically two BES-based grid forming inverters. And it also has 965 kilowatt of distributed PVs, which are basically non-blackstart resources. So when we run the algorithm, it gives you the sequence of the switching for the blackstart. And the scenario, I mean, we have considered a scenario here. So our black start initiates at 8:45 a.m., right? And the transmission grid recovers at 12, which is 180 minutes after the black start initiation. So you can see that in 8:45, two grid forming inverters are started, and they helps to energize the neighboring bus block B11 and B4, forming two microgrids. And then these microgrids expand their boundaries, right, by energizing the neighboring bus blocks, like shown here, and all the way until 9:45, the expansion continues, restoring more loads and bringing more PVs online. And at 10, basically, there's a synchronization. And so the synchronization means two microgrids have been combined. And while this synchronization happens, a grid forming inverter 2, which is GFMI2, changes to non-root generator. Okay, so it was a root generator before. So at 10, it gives off this root bus status for allowing the synchronization to happen. And after that, after the synchronization, it continues in this state all the way until 12. So at 12, you see that transmission grid has come online, but still it's not connected to the distribution system. And at 12:15, the synchronization happens, and grid forming inverter 1 also give up its root bus status. So basically at 12:15, there's only one root bus, which is transmission grid. Okay, and the lastly, a bus block B8 is picked up at 12:30. So this is the whole decision that is provided by the blackstart algorithm. And this diagram shows you the amount of switchable loads that are picked up at various instances and at various bus blocks. So, it shows how much non-switchable loads are picked up and how much switchable loads are picked up. So you can see that switchable loads are picked up at the very end of the study period, that is mostly after the transmission grid comes online. So you can see that most of the switchable loads are picked up once the transmission grid is online. This is because of the finite energy capacity of the BES grid forming inverters. And non-switchable loads, since they are hardwired, they have to be picked up as soon as the bus blocks are picked up. So these are the results in terms of frequency. So when the blackstart was initiated, both the grid forming inverters are operating at 60 hertz, and once they start picking up the loads, their frequency, starts dropping as shown here. And at 10, basically, they synchronize, right? Their frequency got synchronized, and they continue at the same frequency all the way until 12, right? And when they finally get synchronized with the transmission grid, they follow the frequency of the transmission grid, which is 60 hertz. And second figure shows you the Rokov at different instances, and the frequency nadir in the third figure at a different instances. And here Rokov and frequency nadir are both under the security limits. So this is the overall performance of the restoration. So blackstart is started at 845, right? I mean, overall performance, we are looking from the distribution system perspective. So here, this black line represents the peak power capacity. So peak power capacity is around 5, so which is basically the sum of the capacities of the grid forming inverters. And the orange line shows you how the non-switchable loads are picked up, right? And the blue line shows you the total amount of loads that are picked up. And you can see that at 12, right? At 12 to 12, 15 transition, you can see that there is an augment in the total capacity. It's because of the recovery and connection with the transmission grid. And you can see that in the total load, there is a surge in the load pickup because the transmission grid is connected and we are able to pick up all the non-critical or switchable loads. And you can see that there is a gradual decrease in the load as shown here. It's because of the cool load pickup effect. And the third curve shows you the SOC dynamics of the two grid forming inverters. And basically, the fourth or the last subplot is showing how much aggregated EVs are restored in the whole blackstart process. So initially, there was no PV being, no PV are online because they are not able to self-start, right? So once we pick up more bus block, more PVs came online, and finally, when all the bus blocks are energized, all the PVs came online. Okay, so these are the main results, and the conclusion of this research says that integration of DERs helps or makes it possible to blackstart the distribution system while waiting for the recovery of the transmission system. So our framework integrated blackstart capable grid forming inverters with dynamic frequency constraint and helped the microgrid to sequentially expand their boundaries to bring other grid following inverters online. And it also modeled synchronization of dynamically formed microgrids. So the key takeaway from this research is that timely synchronization of dynamically formed microgrids is essential because this helps to augment the total energy and power capacity of the system, allowing them to pick up more loads or greater loads than their individual capacity. So I guess that's the end of the presentation. And utilizing this framework, we have expanded our research. So we have finished two research expanding this work. So first is like allocation of the grid forming inverters and synchronizing switches in the distribution system. And the second is we have enhanced this framework considering the inverse current in a transformer while picking up the bus blocks, and how we can avoid the tripping of the protection devices when we pick up the bus blocks. Yeah. So that's all for my presentation today. Yeah, I will be happy to answer some of the questions, if you have.
Okay, thank you very much. So that was very interesting. So let's go to the online audience. If anybody has question, please unmute yourself.
Is there one?
Hey, Robin, how are you? Good to hearing from you. Yeah, please unmute yourself and ask your question. Cannot hear. Oh, yeah, that's okay.
You're muted.
Yeah, you are muted, Robin.
How about now?
Yeah, that's good. Good to see you. How things are going at your side?
Very, very, very well, thank you. So I have some questions, but also some comments, please. Thank you for the invitation, and very nice to meet you, Salish. My company does grid simulations to train system operators, and we're doing very well with a hypothetical three-phase balance model. We call it Cascadia. We literally train over half the population. We train the trainers who keep the lights on for more than half the United States. And we've been looking for a simulation for unbalanced systems, and we've selected the 123 bus case, just like you have. So I have some quick questions. You're using, let's see, the harmony. What's the, you're using power harmony from the company that makes it in Germany. What's the name?
You mean Dixalen Power Factory?
Excellent.
Yeah.
Do you have a commercial license for that, or are they giving you an academic license?
It's an academic one.
Oh, so you're able to handle this size system with an academic license?
Yeah, I mean, so there are two types of academic license. So one is thesis license. So a student can ask for a thesis license, and this thesis license is like full-fledged license, but you have only for a limited time, like 1 year.
Okay.
And with request, you can extend your license to another year. So that's only for students, and yeah, it's only for students. Yeah.
But that's obviously very powerful, very enabling, because Digilent is one of the few products that lets you go model three-phase unbalanced system with synchronous generator models. Is that correct? Right now. So good choice.
Yeah, you're right.
Well, and then my question is, I really want to. We can't all answer it, but I really do want to work with you and WSU and Iowa State to kind of bring this system alive, the 123 bus system, so it can be used to train system operators, because you've done something that people are not seeing the enormous impact that you can have, where literally several electric vehicles could run a microgrid, a single phase microgrid for a neighborhood, couldn't they? That's with battery storage. And so I just wanted to thank WSU and Iowa State for the invitation, and I really do want to explore Janine, becoming a member of WSU after all this time of your industry consortium and really start taking this to another level. Okay, so and I know the research funding now is very tight and competitive, but this work is absolutely excellent, and I think it really is a good way to go in the future. So and the issue is, my own company can't afford to be paying commercial license fees for thousands of users. The industry, the commercializers of these programs are licensing it per user. Well, we have to build our own software, and we're well on the path to do that. And so I really do want to follow up on some possibilities where we can actually have a three-phase unbalanced power flow that has the dynamics of being able to have synchronous generators at any level in the feeder. And I just want to say thank you for the invitation, and thank you for the really good work
Thank you, Robin. Thank you. Yeah, so actually, we have modeled IEEE 123 bus unbalanced system in the Dixieland Power Factory, and so actually, it's not just about modeling. We have kind of automatized the process of converting any distribution system in the Dixieland Power Factory using a Python. For example, if you give me the tables of any distribution system, so basically I just our Python can read that table and make the elements like the components in the distribution system and connect them automatically. So we have done that. Because it's a painstaking making every component by yourself, so that process we have that.
Yes, we do have a three-phase unbalanced power flow. It's a 3-wire model, but it was written in, I'm going through the process of taking code that's in Visual Basic and coaching others to move it to Python. Python obviously is a very powerful language. So I do want to start sharing that, because that can open up lots of possibilities. So very good. And again, thank you all for the introduction.
Thank you.
Thank you, Robin. Yeah, have a great day. Any other questions? Okay, so then let's go to the room. So anybody has any question?
Yeah.
Sure.
I had a question about the role of batteries in your optimization. I noticed on your graph that specified the state of charge that they started this process essentially at full and ended this process near empty. And so I was curious about for knowing when to start this process. It looked like knowing when the transmission grid was going to be recovered would be an important part of starting this, right? Because if the transmission grid, say, took an extra 30 minutes or so, it looks like they would run out of charge and maybe this process wouldn't work. So was there an assumption that you knew when the grid was going to recover in the beginning?
Yeah, right. So in this study, we know like when the transmission grid will come online. So based upon that information, the SOC of the battery has to be utilized in such a way, right, so that it can sustain the critical loads until the transmission grid comes back. So basically here non-critical loads are sacrificed. I mean, they are not picked up if the problem finds out that the outage duration is long and we need to pick up only the critical loads and sustain them until that point. So the transmission grid outage duration has to be predicted, and this is a deterministic model, right? So we have this prediction model of the outages in our allocation problem. So basically, we have considered the uncertainties of transmission grid outage, uncertainties of the load, and the uncertainties of the DERs to figure out how much sizes of the BESs has to be allocated at what location and where the synchronizing switches has to be deployed, thinking about the meeting the total budget constraint that we have. Yeah, so this has been considered in the allocation problem, but this is just a main formulation problem. So we just consider deterministic cases. Yeah.
Okay, thank you.
Anybody else?
Yeah, I can ask a
Yeah.
question.
Mhm.
Thanks, Elise, for the presentation. So I have one question on, so most of the equation you have just the active powers, right? Is it reasonable to not consider reactive power in this process of like starting?
Yeah, I just saw the reactive power. Yeah, there are reactive power equations considered. So that's if you go to the paper, I mean, we have that reactive power equations there. So basically, yeah, I know you are coming from the capacity constraint of the grid forming inverters, right? So
yeah,
basically, having the finite power capacity, it has to supply active and reactive power, and total power has to be constrained based upon their capacity, right? Yeah, those constraints are considered there in this whole formulation. And I didn't show the results for the reactive power because it will be too much of results to show here. That's why.
okay, I see. Another question I had was on the plot that you showed for the approximation that you make for the synchronization, saying that like you need to ensure that the voltage magnitude and angle should be same when you are synchronizing, right?
Yeah.
And that you approximate with just this power flow. Is that enough? Like how do you prove that this is always true?
Yeah. So so if now I think it's quite, I mean, there's a mathematical proof for that in the paper, but just from the intuition perspective, you can understand this. So let's say if you have two buses, right, and you are going to close these two buses with a let's say with a conductor, right, with a conductor, and when you close this switch, there's no power flow, neither active or reactive. So it means that the voltage and angles are basically same, right? Right. So this is the so but I don't want to make it zero, but I just consider a small power flow like epsilon could be a very small number, right? So that's if you can limit the power flow within a very small number, then the voltage and angles are sufficiently close to each other, right? And so these conditions change the set points of the grid forming inverters. So the grid forming inverters output power and other controllable resources will change to meet this constraint. So so indirectly the voltage and angles are coming closer. Yeah. So I mean this is this I have formulated in terms of planning perspective, but if you want to achieve in real time, you need the feedback of the angles, right?
Yeah.
This is an approximate. I would say this is approximate formulations, mostly suitable for planning, but it may not be suitable for real time implementation. You need a more granular, study to ensure the angles are sufficiently close.
Okay, thank you. There's a follow-up question from
Robin, do you have a follow-up question or that's
Yes,
just?
please. I have a question.
Sure. Yeah.
Yeah. We are still struggling to get an exact match for the the IEEE published 123 bus solution with the right voltages, three-phase unbalanced voltages and angles across the system. Did you start with that? Yes. Did you start with the exact same solution and get a full match with Digsilent for their published solution? And have you stuck with that, or have you been modifying the flows and the voltages, please?
Yeah, I mean, we haven't, okay, to answer your question, so this study is, we didn't implement in a RMS system. So this is a planning study. Yes, we didn't implement this synchronization in a RMS level yet. And our plan is to, to implement in the RMS simulation level, but we haven't done it yet.
Oh, when you get a fully energized system, that's when you'll do the checkout of the two solutions. Is that you're still running islanded systems? Is that right?
No, I mean, what I mean to say is that this optimization problems give you the initial, let's say, initial guideline to blackstart a distribution system.
Okay.
Yeah, so it tells you what actions to be taken sequentially to finally, energize everything safely, right, or securely. But to I mean, to make a synchronization, you need to either have a supervisory action or like some closed loop control action for the synchronization to happen.
Thank you.
But this algorithm is telling at what instant you should take a synchronizing decision. But how it should be done, I mean, should be is not part of this study. Part of this study. Yeah.
Thank you.
Okay. Any more questions? Oh, okay, with that. Okay, thank you very much one more time.
Thank you. I'd like to thank ESIC and WC for the invitation, and I feel happy sharing my research. And if you have any questions, queries, or comments, you can always reach out to me, and I will be happy to help in any kind. Yeah. Thank you.
Yeah, thank you very much. That was very interesting talk. We appreciate the time you had.
Yeah.
That you put on this. Thank you. See you sometime soon.
See you. Bye-bye. Have a good day.
Bye. Bye.